The universe continues to expand at an accelerating pace, revealing more mysteries with every passing year. Back in 1929, scientists discovered something astonishing, that the very elements making up our bodies were born in the fiery cores of stars. This profound realization reframed our understanding of the cosmos, linking human existence directly to the life cycles of stars. By 1957, it became clear that the night sky is not just a beautiful canopy above us, but a powerful display of cosmic forces at work. Despite decades of observation, there's still so much we don't understand. We ask ourselves why we're here, what the purpose of our existence might be, and how stars, planets, and entire galaxies came to be. Often, it's only when cosmic events start hinting at danger that we begin to pay attention. One star that has recently captured the scientific community's focus is Betelgeuse, a colossal red supergiant visible in the Orion constellation. Unlike our Sun, Betelgeuse is not an ordinary star. It's one of the largest known to us, so massive that it makes the Sun appear minuscule in comparison. Yet despite its size, Betelgeuse is more distant than it appears. Located over 640 light-years from Earth. To put that into perspective, even traveling at the speed of light, it would take more than 6 centuries to reach it. And with our current technology, such a journey would take over 12 million years, far exceeding the entire span of human history. Recently, Betelgeuse has exhibited signs of instability. It's been trembling, almost as if warning us of something monumental unfolding within. Although it seems still from Earth, stars are dynamic entities in constant motion. Betelgeuse is known as a pulsating red supergiant, meaning its outer layers expand and contract, leading to noticeable variations in brightness. These changes occur in cycles ranging from a few months to over 6 years. At times, these pulsations are so consistent that scientists can track them precisely. For instance, in February 2021, Betelgeuse's brightness dropped significantly, marking one of the dimmest phases ever recorded in modern observations. This star's brilliant red glow stems from its cooler surface temperature, around 3,500 Kelvin, far lower than the Sun's 5,500 Kelvin. Although Betelgeuse is enormous, its lower temperature means it emits less energy per unit area, which is why its luminosity can sometimes appear inconsistent. Over time, this red supergiant has been relatively stable, but lately, that stability has shifted. It appears to be entering a more volatile phase, and astronomers are watching closely. At the heart of this transformation is a critical process. The star is running low on hydrogen in its core. During the star's life, hydrogen fusion creates helium, releasing immense energy that sustains the star against gravitational collapse. But in Betelgeuse, this supply is dwindling. As hydrogen fusion slows, the star's outer layers expand, making it grow even larger. Helium begins to accumulate around the core, triggering a new fusion process, helium burning. This fusion creates heavier elements like oxygen and carbon, releasing energy in bursts rather than a steady stream. These bursts of energy disrupt the star's structure, causing violent pulsations that expand and contract the outer layers. This is why Betelgeuse's brightness fluctuates so dramatically. During these episodes, strong stellar winds are generated, pushing vast quantities of matter away from the star's surface. As the star loses mass, its internal structure becomes even more unstable, which in turn affects its future evolution. It's a process similar to a giant heart beating irregularly, its rhythm reflected in the glow we see from Earth. To study these dramatic changes, astronomers use a variety of observational tools and techniques. They monitor shifts in brightness, analyze spectral data, and model the star's internal dynamics. Each pulse and flicker brings us closer to understanding the life cycle of massive stars. Betelgeuse might one day go supernova, an event that would release an explosion of light visible even in the daytime sky. If that happens, it would mark the end of a long stellar life, but for now, we continue to watch and learn from this giant, distant beacon in our galaxy. Among the most powerful tools astronomers use to study stars like Betelgeuse are photometry and spectroscopy. Photometry involves measuring the intensity of light a star emits over time, allowing scientists to track subtle or dramatic shifts in its brightness. In the case of Betelgeuse, these fluctuations provide critical clues about the processes unfolding deep within the star. Each variation in light acts as a signal from the star's interior, enabling researchers to observe changes in real time and monitor its behavior over weeks, months, or even years. Spectroscopy, on the other hand, offers a deeper look at the star's light by breaking it down into its component wavelengths. This method reveals vital information about the star's temperature, motion, and chemical composition. When Betelgeuse pulsates, its spectral lines shift, small but measurable changes that uncover what's happening beneath the surface. Through this technique, scientists can trace the rhythmic contractions and expansions of the star's outer layers and better understand the forces driving these movements. By combining photometric and spectroscopic data, astronomers can construct a more complete and dynamic profile of a star's behavior. But observation alone isn't enough. Astrophysicists also rely on advanced computer models that simulate the internal structure and energy dynamics of stars. These simulations incorporate complex equations that account for everything from nuclear fusion at the core to the behavior of matter under extreme pressure and temperature. By comparing observed data with the predictions made by these models, scientists can refine their understanding of how stars evolve, pulsate, and eventually die. One of the most fascinating internal mechanisms observed in Betelgeuse is stellar convection. Deep within the star, energy generated from nuclear fusion must make its way to the surface. This energy moves through convection. Hot matter rises from the interior while cooler matter sinks, creating powerful currents. These churning motions transport heat outward and play a crucial role in altering the star's brightness. As more energy reaches the surface, the star appears brighter. When less energy is transported, its glow dims. These patterns of rising and falling luminosity are what we detect as stellar pulsations. Interestingly, these pulsations are not chaotic. Stars like Betelgeuse, classified as variable stars, follow relatively predictable cycles. As the outer layers of the star expand, its surface cools, and the light we see dims. When the layers contract, the surface heats up, and the star brightens again. This cyclical behavior results from the ongoing battle between gravity, which pulls the star's matter inward, and radiation pressure from within, which pushes outward. When these forces fall out of equilibrium, the star pulses in response, each pulse another clue to its internal life. As Betelgeuse approaches the final stages of its existence, these convective and pulsating behaviors are becoming more pronounced. The star is gradually exhausting the fuel that has sustained it for millions of years. As its core depletes and fusion slows, Betelgeuse edges closer to an inevitable transformation, a supernova explosion that will mark the dramatic end of its stellar life. Until that moment arrives, astronomers will continue to watch its every flicker and pulse, using the star's light to gain deeper insights into the complex inner workings of massive stars across the universe.